Okay, today we're discussing the Henderson Hasselbach equation and how to use it. This question comes from Brown, our textbook, page 727, one of the practice exercises. We're asked in this question to calculate the pH of a buffer composed of 0.12 molar benzoic acid and 0.2 molar sodium benzoate. Here's benzoic acid, here's sodium benzoate. Sodium benzoate is used as a food preservative. The Merck index says its concentration should remain less than 1 part per thousand. It's used in jams and jellies and things like that, bread too. The first thing we're going to do is to solve the equation in the conventional means. We're going to set up an ice table, put in the initial conditions. Here's the acid, here's the conjugate base. The proton, we're going to assume hasn't formed any protons yet because it hasn't dissociated any of the acid. We're going to pretend that an amount X has dissociated of the benzoic acid, so that our equilibrium is 0.12 minus X, which is going to generate more benzoate anion, so that's going to increase the concentration of benzoate by plus X, so the equilibrium is 0.2 plus X, and the proton concentration is going to go from 0 to X. That gives us all three equilibrium conditions, and we'll set up our equation. Ka is equal to 6.3 times 10 to the minus 5. Here are the equilibrium concentrations. We set up the trinomial, and I forgot to write equals 0. We plug it into our calculator using the quadratic formula. We discard the negative value, and we get that the concentration of H plus is equal to 3.7 times 10 to the minus 5, which gives us a pH of 4.42. Then we use the Henderson Hasselbach equation to solve the same problem. We'll see that it's a much shorter solution. The Henderson Hasselbach equation, it says that pH is equal to pKa plus the log of the conjugate base concentration divided by the acid concentration. When we plug in all the values, we get the same number, 4.42, much shorter. If we can recognize a buffer system, then we can go straight to using the Henderson Hasselbach equation. It's a much quicker way of calculating the answer. On page 730, we have another buffer system. This time it's acetic acid and the acetate anion. But in this case, what we've done is we've added 0.02 moles of strong acid, HCl. And we've asked what's the pH, what's the effect on pH from the addition of this strong acid. I set up an ice table. I show the chemistry. Here's the acetic acid, the acetate ion, and the H plus concentration, which we're going to calculate. The ice table just helps us to keep all the quantities straight. At the outset, we have 0.3 molar concentration of acetic acid and 0.3 molar concentration of its conjugate base, the acetate anion. So we definitely have a buffer system. We have an acid and its conjugate base in the same solution. By the addition of strong acid, what we're going to be doing is protonating the acetate anion. So we're adding a hydrogen to acetate, which is going to turn it into acetic acid. So the effect is going to be that it decreases the concentration of the acetate ion by the same amount as the amount of strong acid that you've added. We've added 0.02 molar concentration of strong acid, so that brings our acetate ion concentration down. What did I write here? Added HCl. It should be the other way around. I just wrote it upside down. This decreases to 0.280. And this one, that's what you said, that's what you mentioned earlier. Okay. Okay, right. Did I enter the concentrations correctly here? No, I have them upside down in here as well. So it's 0.28 for the conjugate acid, 432. Net effect, I think I may have entered it correctly in the calculator, I just wrote it wrong on the board. What it's going to do is it's going to lower the concentration of acetate anion down to 0.28 while increasing the concentration of acetic acid to 0.32. And then when you enter the quantities in, it'll be the log of 0.28 over 32. Let's just double check that before we continue. The log of open bracket 0.28 divided 0.3, close the bracket, gives you negative Right, so it decreases the number from 4.74, which is the pKa of acetic acid. It will bring the pH down to 4.68. You notice that it makes a small change in the pH, as we would expect, because it's a buffer system. It buffers the presence of the acid. Now look what would happen if we added the same amount of acid, 0.02 moles per liter, into distilled water, enter that into the pH equation. pH equals negative log of H plus 0.02. You get a pH of 1.7. So the buffer has a definite, a very strong buffering effect, preventing the pH from going down too low. Right, today we're also going to mention titrations. Titration is the process of reacting a solution of unknown concentration with one of known concentration, which is known as a standard solution. We could extend the definition to say that in medicine it is the practice of administering increasing doses of a medication until a wanted physiological response is achieved. So for example, if you're suffering from pain, they'll titrate you with pain medication until the pain is controlled. So the definition of titration in a strict chemical sense is to use a standard solution and then to titrate it with an unknown reagent to find out what the concentration of the unknown reagent is. If we have a strong acid with a strong base, when there is a neutralization, the pH will be 7, because the bases, the strong acids and strong bases, will produce a salt and water. So here we only have to worry about the concentration of an excess of one amount, or if there's a slight deficit. That's what's going to affect the pH. Two things you have to keep into account when calculating the pH of a reaction between a strong acid and a strong base. Take into account the hydroxide or proton concentration and the final volume. On page 734 of our text, practice exercise, section A, we have a potassium hydroxide solution being titrated with, I think, nitric acid. I forgot to write down which acid it is, but it's a strong acid. And 25 mLs of the hydroxide solution, which is 0.1 molar, is going to give you 2.5 times 10 to the minus 3 moles of hydroxide. And it's titrated with 24.9 mLs of, again, a 0.1 molar solution of a strong acid, so that after the reaction you have 1.0 times 10 to the minus 5 moles of excess base. So what is the concentration of the hydroxide? It's going to be 1.0 times 10 to the minus 5 divided by the total volume of the two solutions that were added, 25 mLs of one and 24.9. So the total volume of the solution will be 49.9. That's where we find our concentration, which is 2.04 times 10 to the minus 4 molar for hydroxide. Then we take POH is equal to negative log of OH concentration. We have a POH of 3.69, and by subtracting that 3.69 from 14, we find out that the pH is 10.31. Just keep in mind when doing these calculations that if you have the pH change is going to be very rapid at equivalence, because there's no buffering effect. In later examples, we're going to see what happens when you mix a strong acid with a weak base, or a weak acid with a strong base. You'll see that the results are not going to give you a pH of 7.